So today we're going to finish up section 6. Yes? No. Okay, so this is not on tomorrow's quiz. Again, the quiz is only on R.5c and R.5d. It's adding and subtracting rational expressions and complex fractions. So let's see what we're going to be doing today with these rational exponents. So again, here is a screenshot of my textbook. Again, if you don't want to open up the document, you could always read through their explanation, but I'm going to explain everything. So what we're going to be doing with the rational exponents or these fractions is we're going to be turning them into roots. So here is, again, a review of definitions and rules for exponents. Towards the end of the examples I do, again, I'm going to be reviewing when we multiply powers that have the same base and when we divide and apply this quotient and product rules. So here is my first example. I've got the square root of 4. And notice the little one I've included. I've included the exponent. Now, technically, whenever it's an exponent of 1, I don't need to show it. Same thing with the square root. When you see this symbol, the radical with a number in it, and it doesn't have the little number that's right here, this is called the index. If there's not a number there, then it's a square root. If there were a 3 there, like in this example, it would be a cube root. So let's go ahead and take a look at the first example, and I'm going to show you how we're going to turn this square root into a fraction exponent. So what we do is we take the index, or the root we're finding, and it is going to be the denominator of our fraction exponent. And then the exponent is the numerator. So if it helps you to think about a tree that grows outside, think about where the roots are located. They're located down at the bottom of the tree. So the root of this problem is the denominator of the fraction. It's the bottom. So the denominator of your fraction exponent is the root, and the numerator is the exponent. So if I ask you to evaluate this, the square root of 4 is 2. The exponent that's on there is 1, so it's just 2. Same thing for the cube root. If I ask you to turn this into having a rational exponent, again, you take the index or the root that you're taking, it becomes the denominator, and then the exponent is the numerator. We can also solve this, and you should know that 2 times 2 times 2 is 8. If I have just a variable, again, this is the root, this is the exponent. So you take the number that's under the radical symbol and raise it to the b over a power. So we're going to practice this. Now, when we're doing these, we want all of our answers to be written with positive exponents. So yesterday we saw that if it had a negative exponent, we turned it into a fraction, or we thought about reciprocal. Also, right now, for our purposes, we haven't learned about imaginary numbers yet. So all the numbers that are going to be under a even root, they have to be positive numbers. Okay, we haven't learned how to take a negative square root yet. Okay, we're going to be learning that coming up, and that's going to give us an imaginary number. So for right now, we're only dealing with real numbers. So I'm going to be giving you questions with a rational exponent, and I'm going to ask you to simplify these. So again, the bottom number is the root, the top number is the exponent. So I'm going to turn this into a square root, and then I'm going to raise the answer to the first power. So the square root of 4 is 2. Raised to the first power is just 2. For the next one, I take the 27. It's going to go under my radical sign. I'm going to be taking the third root. That's my denominator. After I find the third root, or the cube root of 27, then I'm going to square it. So the cubed root of 27 is 3, and then I square it, and I get 9. Now, don't try to rush and do things, super fast. Just take your time. Good? Okay. All right. So, negative exponent this time. Everybody remember what happens when we have a negative exponent? We flip it to the reciprocal. So what we're going to do is we're going to take this 81 to the 1/4 power and we're going to put it underneath a 1 because we're flipping it to the reciprocal. And let's just take our time here. We're going to, actually let's do this. Let's first put it underneath the 1, take away the negative sign. Then next what I'll do is add my radical symbol. And I'm looking for the 4th root of 81. So I have to figure out what number times itself 4 times, gives me 81, and that number is going to be 3. And again, if it's got a 1 in the numerator, know that we don't need to actually show it there. Okay, so we will not be using calculators, so you will have to be able to do these without calculators. The numbers aren't going to be that huge, so they'll be doable without a calculator. All right, so now the next one, again, notice my numerator is not a 1 this time. So after I find the 4th root of 16, I have to cube that answer. So I'm going to take 16. I'm going to be finding the 4th root, and then I will raise that answer to the 3rd power. So here I'm going to do the 4th root of 16, which is 2. And then I cube it, and I get 8. Let's try the next one. Another negative exponent. Again, let's not try to do too much too fast. Let's go ahead and first turn it to its reciprocal because it's negative. So I'm going to write 1,000 to the positive 2/3 power. Then I can put in my radical. I'm going to be finding the cubed root of 1,000 and then squaring that answer. So the cubed root of 1,000 is 10 because 10 times 10 is 100 times 10 again is 1,000. And then I square the 10 and I get 1 over 100. The next one, again, be careful with your negative bases. This 100 is the only thing that's being raised to the 1/2 power. So when I go to do this, the negative sign is going to be outside of the square root. And then I would simplify this. So the 2 would go here, and then I could put the 1 there, but I don't need it. So then this just becomes the negative sign is there, and then the square root of 100 is 10. Now we're going to see an example when it's in parentheses in a square root, and this is what I was talking about, the imaginary numbers, but I'm going to show you, I think it's in like 2 examples. Now, however, if it's an odd exponent base or an odd root, can move this. So if this root is an odd number, I can find the root of a negative number. So again, negative 64, notice it's being held with the parentheses, is under the radical. I'm finding the cube root of negative 64, and then I'm going to square the answer. So the cube root of negative 64 is going to be negative 4, because negative 4 times negative 4 is positive 16, times another negative 4 is negative 64. Now that I've found the cube root, now I square the answer, and it's positive 16. The next example is the trick. Notice this time, I just did this problem. I did negative 100 to the 1/2 power with no parentheses. Whenever you have a parentheses around a negative integer, then, and you're trying to do a square root or a 4th root, right now, for us, we can't do it. And that's going to be your answer. Okay, we're going to learn later on that this answer is going to become 10i. We're going to learn about the imaginary number of and it's going to be represented by the letter I. But for right now, we only want real answers. So this is only when there's a parentheses around a negative number and the root is an even number. We can find the root, the cube root of a negative number. We just did it with the negative 64. So we can find the root of a negative integer when it's an odd root. Let's try the next example. 27. It's under the radical with the cube root, and then I'm going to raise the answer to the fourth power. So the cube root of 27 is 3. Raised to the fourth power is 81. The next one, the root is a square root because it's a 2. And then I'm going to raise it to the third power. So the square root of 64 is 8. And then I cube that, and I get 512. Now, I could do the exponent first and then the root, but the problem with doing the exponent first, like if I tried to do 27 to the fourth power and then try to do the cube root of that, and I'm not using a calculator, it's going to get really large. Sometimes you may have to do that because maybe they're going to give you a number that you can't find the cube root of. But once you square it or cube it, then you can probably do it. So sometimes you may have to do the exponent first, but generally it'll be faster and easier if you do the root first and the exponent second. But we could do the exponent first and then the root second. Let's try another. Again, notice the root is an odd number, so I can find the fifth root of negative 32. However, notice it's a negative exponent. I need to make it a fraction or the reciprocal first. So I'm going to move the whole thing underneath the 1. I'm going to make my exponent positive now. And now I'll turn it into the radical symbol. Again, the 5 is an odd number, so I can actually find the fifth root of negative 32. After I do that, I'm going to raise it to the fourth power. So the fifth root of negative 32 will be negative 2. I'm going to raise that to the fourth power. And 2 times 2 is 4, times 2 is 8, times 2 is 16. Yesterday we saw that when we have a fraction raised to a negative exponent, we just flip it to its reciprocal. So that's the first thing I'm going to take care of, is making that exponent positive, flip it to the reciprocal, and now my exponent is positive 3/2. Again, the denominator is the root, so I'm going to be doing 100 over 121, finding the square root, and then cubing the answer. Now remember, you can pull this apart and find the square root of 100 and then the square root of 121. Square root of 100 is 10. Square root of 121 is 11. And then I'm going to cube those. So 10 times 10 times 10 is 1,000. And 11 times 11 is 121. Times 11 again is 1,331. Final answer. The next few examples are just applying those exponent rules and properties that we learned back in R3. So we'll practice those, but they're going to have fraction exponents. So notice here, we're going to apply the product rule. Remember, when the bases are the same, you keep the base the same. Okay, so when the bases are the same, we don't multiply the base, we keep the base the same. and we add the exponents. So we're going to add 4/3 plus 2/3, and that's going to give us 6 to the 6/3 power. I can reduce 6/3 and make it 6 squared, which equals 36. So remember, when you multiply, you add the exponents. When we divide, we will subtract the exponents. So this one will become 7/3 minus 5/3, and I'll get 2/3. So this will turn into 125 to the 2/3 power. We subtract those exponents, and now we can evaluate this. Again, the 3 is the root, the 2 is the exponent. The cube root of 125 is 5. Raise that to the second power, and I get 25. Yes. Okay, so for number 13 again, when we multiply numbers that have the same base, we take their exponents and add them. So I'm going to add 4/3 plus 2/3. When you add fractions, you keep the denominator the same and add the numerators. I now can divide 6 by 3 and get 2. So now this problem will become 6 to the second power, which equals 36. Good? Yes?
What happens if you have a different denominator?
Then you got to find a common denominator.
And then you just add from there and then simplify down?
Correctly. Yes. So yes, if it doesn't already give you a common denominator, you have to find it. Yes?
You can't cube root 6, but if you were able to, wouldn't you know you do that first?
You could, but most of the time it's going to be something that you cannot find the root of. So it'll be easier if you add the exponents. All right, let's try another example. Everybody good on the division one? We subtracted those exponents, and I did 7/3 minus 5/3, and I got 2/3, and then I can find the cube root and then square it. The next one is just a variable. Again, we're multiplying these two. So again, we're going to take the exponents and add them. So I'm doing -8/9 plus 17/9, which is going to give me 9/9. And then this would simplify to 1. So my answer here is r to the first power. Or you don't even need to write the 1, it's just r. All right, next one, we have some options here. You could either add that denominator's exponents, but I think what I'm going to do is, so I'm not dealing with a negative number on the bottom, I'm going to move the z to the -2 power. I'm going to move it to the top to make it positive. So I'm going to rewrite this as z to the 3/4 times z squared over z to the 5/4 power. Next, what I'm going to do is add the numerator exponents. So here we go. This does not have a common denominator, so I need to find a common denominator. So I'm going to be adding 3/4 plus 2/1. So I would find my common denominator. It's going to be 4. So this would become 8/4. So this would give me 11/4. So the numerator is now z to the 11/4 power. I'm going to rewrite the denominator. And now for division, you subtract. So I'm going to subtract 11/4 minus 5/4, and I get 6/4. And then I'm going to reduce this to 3/2. So my final answer here is going to be z to the 3/2 power. I can leave it in exponential form. I don't need to write it as a radical. Now, if at the beginning, if you would have preferred to have added 5/4 plus -2 and found a common denominator that way, you could have. But I think it's a lot easier just to make all your exponents positive first and then work on combining. All right, for number 18, notice we have a power to a power this time. So remember, this power of 15 is going to go to the 1/5, and it's also going to go to the 2/3. So I'm going to multiply. When it's power to a power, you multiply. So it's 1/5 times 15/1. I can simplify. And the power on my R is 3. Then for the S, I'm going to do 2/3 times 15/1. I can simplify this, make this a 1, a 5, 10/1, so it becomes S to the 10th power. I'm going to write the R squared in the bottom, and now I just need to simplify. I could either subtract 3 minus 2 and get R to the 1st and S to the 10th. Or I could just say, take away 2 from here and 2 from here, and you're left with 1. So final answer is just R times S to the 10th. The last one is also a power to a power. So again, I'm going to multiply 1/4 to 3. So this will become P to the 3/4 power. Multiply 2/1 times 5/4, and it becomes P to the 10/4 power. Again, when you divide, we subtract the powers. So 3/4 minus 10/4 gives me -7/4. So now my answer looks like this, but the instructions said to write all answers as a positive exponent. So I'm going to move it under a 1 and make this 7/4. Say 2 to the 3rd times 3 to the 2nd. I can't add these exponents. I would have to figure out that 2 to the 3rd is 8 and 3 squared is 9 and do it this way. So the only time you add the exponents is when the bases are the same. Okay, so that's what she was asking about that. So when you multiply, the bases need to be the same and you add the exponents. When you divide, you subtract. All right, so let's start the problem over again. So we have P to the 3rd raised to the 1/4, and then P to the 5/4 squared. So the first thing I'm going to do is take care of the power to the power. So I'm going to make this P to the 3/4, because I multiply, and P to the 10/4. Now, just like when we multiply, the base stays the same. So I'm not getting P divided by P is 1. So really what I'm doing here is P to the 3/4 minus 10/4 power. It's not as a fraction, it's just sitting there as like a whole number. Okay, and then now I would subtract, and then I end up with P to the -7/4 power. Whenever it's a negative exponent, we would take that, think reciprocal, put it underneath a 1, and make it positive. Does that answer your question?
Yeah, I just thought that instead of it being 1/p to the 7/4, it would just be p/1 to the -7/4, which is not right.
Right. So you have to make the exponent positive by putting it underneath a 1. Think reciprocal. Okay, and homework is due Monday. You have a quiz tomorrow on adding and subtracting and complex fractions. There is a review. It's on Canvas. It's got 10 questions. I will be posting a solution file later on today. You do not need to turn this review into Canvas. The quiz will have more adding and subtracting than complex fractions, so it'll be heavier with adding and subtracting. And those are the two concepts. If you go back and look at the notes, it's R5C and R5D. That's it.